Welcome back. We're going to go further down the rabbit hole this time by looking at how to describe and present your data. In this podcast, we're going to look a lot at terminology surrounding different kinds of data and how you can best render it visually. Before we go any further, I want to thank Dr. Raj Sharma for allowing me to adapt a presentation that he gave on this topic for the purposes of this podcast. When we're looking at a research question, at the most basic level, you'll have inputs and outputs, or independent and dependent variables. Variables can be anything at all, but they result in data that needs to be described and analyzed. Variables can be numerical, that is, they consist of numbers. The first type of numerical data is one that you should all be well familiar with. A continuous variable can have any of an infinite number of values and are not restricted to whole numbers. Examples of these include height, weight, hemoglobin, or temperature in kelvins. In contrast, discrete numerical variables have to be whole numbers, which limits their possible number of values by definition. These are usually represented by counts. Examples include number of patients with disease type, number of adverse events, or in this instance, number of ducks in the box. We then move into something called categorical data. In its simplest form, you have binary data. There are only two options. In this instance, your options are either alive or dead. If you have more than two categories, you're no longer looking at binary categorical data. Here you can have as many options as appropriate, but there's no hierarchy. For example, in this graph, we can see third languages spoken by state. Hair color and eye color are other examples of this. If your categories are not equal, but have a meaningful order, this is a different type of data again. Sometimes it's also called ordinal data. In our example here, we have levels of education. Obviously, a doctorate is a higher level than high school, but the incremental increases aren't uniform between categories. If we put all this information into a table, you'll be able to see and compare our data types. Note that some of the previously common binary examples are getting a little bit more complex, and they may end up shifting categories. Of course, there is more than one way to look at these categories. If we rejig the table a bit, we have another way to consider data. Our unordered categories can also be called nominal data, and our ordered categories can also be called ordinal data. When we look at numerical data, the categories are interval and ratio. Interval data can be continuous or discrete, with the values equally spaced along a scale. However, the 0 point is arbitrary and could be changed. Examples of this would be the Celsius temperature scale, in which we've all agreed to have 0 being the freezing point of water and 100 degrees to be the boiling point of water, give or take. If we selected a different 0 point, we would still have a scale to work with. Another example is an IQ score, in which 100 is defined as the mean score in a given population. It can move. Finally, ratio data is the continuous numerical data that we most easily recognize. Like interval data, the values are equally spaced, but here, 0 is not subject to debate. Examples of this include things like height, weight, hemoglobin, or plasma sodium. The good news is that interval and ratio data are often treated the same. So you might wonder why you should care about labeling your data types. Well, this is actually a critical step in preparing to analyze your data, since data type is an important factor in selecting an appropriate statistical test. For example, categorical data is non-parametric, while numerical data is often parametric. There are nuances to this, but it's beyond the scope of this podcast. For categorical data, tests such as chi-squared or Fisher-exact tests will potentially be used, while for numerical data, t-tests or ANOVA analyses could be used. We'll unpack this a little bit more in future podcasts. The other reason why you might care about what kind of data you have is that it can influence how you present it visually. There are several reasons why graphing data can be very helpful. First, it allows you to take raw data and see patterns more easily. Second, you can describe a large amount of information in a small space. Finally, it's an important tool of presentation and communication. Data tables are not always efficient communicators. Our first type of graph is called a histogram. You can use these with any type of data. What you're wanting to do is look at the distribution of your data. On the x-axis, you place your values or categories, and on the y-axis, you have the number of counts of each. With numerical data, you can use all possible values if they're discrete, or you can group possible values, especially if they're continuous. In this example, only integer scores were possible, so I've plotted all possible values on the x-axis. You can see here that the distribution favors lower scores. Another type of graph that quickly shows the distribution of data is a box and whisker plot. This shows the median, 25th and 75th percentiles with the interquartile range, and also the highest and lowest value in the sample. Both of the previous graph types look at distribution of data points. Not all data follows a symmetrical bell curve, but may display something called skew. In a perfectly normal distribution, the mean and median are the same, which you can see in these graphs. If there is skew, they are not. In a skewed distribution, using a mean and standard deviation may not be as descriptive as using a median and interquartile range, and these box and whisker plots and these frequency plots demonstrate this nicely. If you're working with categorical data, bar plots may be a good option. In our example here, we've got individual surgeons on the x-axis with counts of men and women on the y-axis. We can make quick comparisons within and between categories. If you've got a couple of numerical variables that you want to assess for a possible association, a scatter plot can be a good option. By convention, your independent variable goes on the x-axis. In this example, we're looking at PCS scores by patient age. I've put a trend line in here, but it's pretty clear that there's no useful association. Finally, if you're working with categorical data and an exposure, intervention, or event has occurred, a contingency table may be quite helpful. Exposure is placed in the rows while the outcomes go by column. This lets us see that use of spring water is the least common choice in each of these 3 villages. One more summary table. For symmetric continuous data, mean and standard deviation are the descriptors of choice, and you can use histograms, box and whisker, and scatter plots for display. For skewed data, the same general principles, but then you'd use medians and quartiles. Finally, for categorical data, frequency counts and percentages are the choice descriptors, with bar plots and contingency tables for graphic display. Correctly describing your data will help you both with planning your future analysis and with finding efficient and accessible ways of presenting your data visually. In the next podcast, we're going to take the principles learned in this and the previous podcast and get down to selecting statistical tests.